using the arrow key. Oh, it was supposed to be late last night. It was early this morning. So tonight's program, give you a lag here. So just all finished dinner. I'll have a little roundup of Australian Space Association news. And then we're going to jump straight into our guest speakers. We've got 2 guest speakers here in the room in Melbourne and another one coming in from, I think, Queensland. Is that right? New South Wales. Right. And then I've got a quick roundup of Australian and international space news. And then we've got a planetary and space science update with Professor Andrew Rennie over here. And I've just promoted you. And then we theoretically are out of here by 9:15 if all goes to plan. So just a bit about us. We're a completely volunteer group. I'm the president, Peter, the president of the Space Association. We've got a number of members around the country. We run various activities, including obviously tonight's meeting, which we live stream and have in the room as well. We also run a weekly radio show on Southern FM, which live streams and podcasts, which gives you a good roundup of news, both domestic, international, and historic. And once again, once that's completed, the podcast goes up usually the next day, the Thursday. The show's on every Wednesday, and the podcast is usually up on Thursday or Friday. All right, so just a quick roundup of Australian Space Association news. We did run a member survey, which closed last month. Myself and a few other people had a few things go on in the month of June, so we weren't able to actually get a committee meeting together to look at the results in any kind of detail. We didn't have the final results at the last meeting. We do have those in now, and we've got a summary of all the results, which are going to be, which has been circulated to the committee, and we're going to be then looking at all the things that have been asked, suggested, objected to, comments, feedback. Some of the things we've already implemented, like some changing the audio configuration tonight. So we do hope that's better for everyone, both in the room and online. And then we aim to update you all as members in July with what we're going to do, what we propose to, what the committee would recommend we do. And we had the AGM last month, and we're delighted to welcome Naomi Campbell to the committee. So here's the new committee. So a lot of same old faces, but once again, Naomi has joined us as our first female committee member for decades, and lovely to have a breath of fresh air. So if you're online, Naomi, welcome. All right, so once again, the Space Association is a non-profit volunteer group, all run by volunteers, and also basically supported by the memberships that people do pay. And we certainly do appreciate everyone for their continued support. I think a lot of renewals have been sent out, and I think most of them have come through as a return, so I appreciate that. If you've lapsed, we'd love you to come back. If you know somebody who'd be interested, we'd love to have them on board. We do have full memberships and also concession memberships for students and old people like me and other people. So have a look at that. All right, and our meetings as tonight, we are currently at the Golden Gate Hotel in South Melbourne. Our meeting formula, if you're not sure exactly, essentially it's the fourth Monday of every month, apart from December. So if you do the nuts and bolts, the calculation, 25th of July is our next meeting here at the pub, if everything goes well with our COVID situation. I like this picture. All right.
Yeah, so we're just going to run through Spiral Blue, just do a quick company overview. And then Shoaib's going to take over and give sort of a company overview for his company, Esper, and then talk about the actual Rainbow Python project that we're collaborating on. May is actually going to present for us tonight, so I'll hand over to her. And yeah, go for it. Thank you.
Can you guys see my slides all good?
Yep, we can see them.
All right, sweet as. So my name's May. I'm a business development intern at Spiral Blue. I'd just like to send apologies from our CEO, Taufik, who couldn't make it tonight because he's picking his wife up from the airport, who he hasn't seen for 6 months. We're also joined by our CTO, James, who will answer some more technical questions later. So a little bit about Spiral Blue. We were founded in 2018 with the goal of making Earth observation more accessible. We're committed to providing the right information at the right time from space. So we do this by putting computers on satellites, such as through our partnership with Esper. We're so thrilled to be working with them and very grateful to have been invited to give this talk. So why do we do what we do? I mean, first of all, space is really cool. There's so much more outside of this funny little ball that we all live on. But we can also put satellites outside of this funny little ball and use them to help the world. So Earth observation is kind of like taking a selfie, except this selfie has applications in so many industries such as defense, agriculture, emergency services, maritime, financial services, and insurance. So since being founded in 2018 by our CEO Taufik, CTO James, and Head of AI Henry, we've since expanded to a team of over 7 engineers, developers, and scientists. And we're so proud that in such a short amount of time, we've been able to secure $1.6 million in funding, complete a defense contract, and deliver 3 space missions. So one of the problems facing Earth observation is the bandwidth problem. Satellites produce copious amounts of data and we just can't keep up with it. The amount of accessible data is significantly smaller than the amount of data collected. So for example, a satellite that might cover 6 million square kilometers in a day might only be able to send back 20,000 square kilometers. This results in higher costs, higher minimum order quantities, and longer lead times, which just makes Earth observation expensive and inefficient. For example, if you wanted an image of your house today from space, your only option might be to purchase an image of your entire suburb, including your neighbors' houses, what they've been up to. At the end of the day, it's just inefficient, expensive, and prevents Earth observation from being readily accessible. Another problem that exists in Earth observation is just what do we do with this data? At the end of the day, customers don't want data. They want the information from the data in order to make better informed decisions. So imagine you wanted to find out if it was raining tomorrow and you had to go through radar data. Look at the temperature over the Pacific Ocean at a particular time. Look at wind data and process all of that on a computer, all just so you can decide if you want to bring an umbrella with you tomorrow. I don't know about you, but it sounds a lot easier to just get your phone out and check the weather app. Data processing can be tedious, so what do we do about it? At Spiral Blue, we're solving these problems with our Space Edge services by conducting onboard image processing using our Space Edge computers. By only sending what you need, we've reduced data costs by a factor of 10, which also allows us to offer a service with no minimum order quantities. We deliver information to customers with a user-friendly platform, which increases accessibility to Earth observation and enables further applications. Space Edge services can streamline the process of going from data to information to a better informed decision. This reduces lead times from weeks to hours. At the end of the day, Earth observation can't really be useful if you can't use it. So we've made this process simple by allowing you to simply choose what and when you'd like to see, choose what you want to do with the images, and provide user-friendly information to make better informed decisions. So we can help you to find out what you want, when you want. So you might be thinking, this is a lot of talking, how are you going to do it? So we've taken cutting-edge computing technology and adapted it for the harsh space conditions through thermal control and radiation protection. We also provide a secure and accessible platform for you to run your software on our computers in space and be assured that your information and intellectual property is protected. We've also developed proprietary machine learning architecture, which is 50 times smaller than state-of-the-art. Again, reducing lead times from weeks to hours. We're pushing the boundaries of technology to provide you with easier, cheaper, and more efficient access to Earth observation. In the short time since our founding, we are so pleased that our work has been recognised through winning the Gravity Challenge, Maxar Spatial Challenge, and Waratah Seed Competition. And we'd love to partner with you to provide the right information at the right time in space so that together we can make the Earth a better place. So that's it from me. So I'll hand over to Shoaib to talk a little bit more about Esper and Rainbow Python.
Hi there. Just while we're doing the transition, for the people in the room and also online, we'll have questions at the end. If you're in the room here, you have to come up to the microphone here and ask your question. There's no in-room microphone there.
All right, so you should be good to go. So cameras there, microphones there.
Sounds good. Thank you. Thanks, May. And good evening to everyone here. Thanks a lot for having us. So I'm Shoaib. I'm the CEO at Esper Satellite Imagery, and we're a company that's delivering climate data from space for industrial efficiency on Earth. Just gonna figure out how to actually change the slides.
Sorry, a few seconds. There you go. And there, okay, should work.
Awesome, thank you. So just a little bit about myself and just about the team that's working on it. So my background is in space science. That's where my academic background comes from, and I've been working as a payload engineer across multiple high-powered rocket teams, building payloads for them. So building everything from sounding rocket payloads to image, basically do experiments in microgravity and image those changes, all the way to building the imaging systems for those payloads for more observation-focused applications. My CTO, Joey, he's a mechanical engineer. He's previously co-founded a medtech startup that was also focused on medical imaging, and he's a 3-time hackathon veteran, and he's won a bunch of hackathons as well. And at Esper, we're specifically focusing on a lot of climate-focused applications for Earth observation. One of the ones that we're looking at are methane leakages and methane emissions coming from fossil fuel, basically from the fossil fuel industry. So the oil and gas industry leaks methane from their oil and gas pipelines during those the transition periods when they're transporting resources around, and that actually causes 90 times more pollution because methane is a gas that is 90 times more potent than carbon dioxide, contributing to more and more global warming. With mining exploration as well, specifically looking for green metals, looking for metals such as lithium, cobalt, gold. Those processes take quite a bit of capital and quite a bit of surveying to actually find those mineral deposits, which themselves have a huge climate impact, as well as they disturb the geographies and the geologies of the places where we are to actually prospect and excavate those minerals. This is a problem that's specifically faced with these green minerals, as we call them, stuff that's powering our modern day electronics, all the way to stuff that's going to be in our batteries for our electric cars. And just moving beyond that, now talking about the emissions in the atmosphere when it comes to actually sucking them out of it, working with carbon sequestration specifically, it's much harder to track it and much harder to incentivize carbon sequestration, especially when it happens in farming, forests, and coastal ecosystems. And to track this data, there currently are very little data sources to accurately track that. And recently, even the Australian government has been investing a lot of money in specifically into carbon sequestration projects, just to have better climate data of these projects to better incentivize the people actually doing the sequestration for them, from everything from farming to forest to more forestry focused projects. To basically build a solution to these problems, which essentially is a lack of data for these problems, we're building our own network of satellites that will be capturing imagery of the Earth's mass, specifically chemical data, everything from the chemical compositions of the atmosphere to the chemical compositions of the Earth's landmass. We're going to be using it to track atmospheric greenhouses, soil carbon concentrations, metal mineral deposits, and so on and so forth. We're essentially building a pulse monitor for the Earth, filling in this white space of the intelligent data for the industries and the problems that I've just talked about. We're building this by utilizing hyperspectral imagery. It's an imaging technique where we essentially look at hundreds of wavelengths of light to essentially do spectroscopy of these stuff that we're looking at. And in our case, it's Earth's landmass. Being able to tell how different wavelengths are absorbed and reflected for different minerals across a large spectral range can essentially becomes a fingerprint for these specific minerals, allowing us to detect them. So here's just a cool picture of an apple just being in different wavelengths, how we can detect rot, even when in looking at it visually, we cannot, just being able to tell how the health of this certain object is. And that's how we sort of extrapolate to the rest of the planet. Instead of an apple, we're going to be looking at rot that's growing on the Earth. Now, just going deeper into the applications that we've been working on. So specifically with those problem sets, we're looking to track soil and atmospheric carbon. We're looking to explore and track green mineral excavation, and where we have huge use cases within agriculture as well, where we're looking to map out accurate soil and crop metrics. And we've basically estimated working a lot with these industries while we've been making them more climate efficient, making them more climate friendly. We're also looking to be saving them a lot more costs just in general, just by adding more data into the daily processes, increasing their overall efficiencies. Currently, we have around 78 million USD in letters of intent. So these are customers we've already signed agreements with. We have a mining project that we're currently working on with a mine based out of Western Australia to look for gold, nickel, and copper. And some of our early customers that are here, we're working with Kava Space. They're an Indian-based company that's working on agricultural solutions. They do agricultural solutions for almost half of the planet at the moment. I think they're working with at least 2 million square kilometers at the moment. We're working with Datia Earth. They're a finance customer. They're looking at tracking metal exports, imports, and productions, basically for commodity traders. And we're also working with Swan Systems, who are Western Australia based, who are looking essentially at tracking irrigations across larger farms. So that's a bit of a company overview, and sort of how our history sort of begins is from just these two images here. The company was started as a hackathon project. That's me, my co-founder Joey, and a couple of other people who helped us along the way. We essentially built something slightly different. We were building an AI that could help design satellites or satellite payloads. And is the sound still going through?
Sorry, Aisha, might have you set up. I'm not sure what's not.
Something broken while I've been gone.
Yeah, I moved this off. I was thinking I was just helping out. As per usual, I did.
All right.
Sorry.
All good, all good.
Sorry, I just wanted you to see.
All right. Keep talking.
All right, hopefully, all right, that should work. Cool. Sweet. Yeah, so these two images are essentially how Esper started from a hackathon project. And since then, we've basically became a garage startup. This is us building our first hyperspectral sensor in my co-founder's kitchen. We did not have adequate access to lab spaces back then. This picture is probably 2 years-ish old. And that was what we call our V1 or the version 1 imager that we ended up building. But now we've sort of scaled up to have a proper lab and a clean room, and we've done a number of aerial tests of the same imager that we're going to be launching soon. So we've done a number of our agricultural pilots, and those are the same similar pilots we're going to be doing with our mining customers and the customers we're lining up as well. And for, I guess, the future of the company, as we're working with these aerial pilots and the launches that are coming up that I'm just going to touch on in a bit, we're looking to build an entire constellation of 18 satellites. And with those full 18 satellites by 2025, we're aiming to get to a global daily coverage. Essentially, we want to be capturing capturing pictures of every point on the Earth on a daily basis, and analyzing them from a spectral point of view, basically having chemical compositions of every point on the Earth on a daily basis. And that's a pretty good segue into the stuff we were working with Spiral Blue with on. So Project Rainbow Python is a collaboration between 4 organizations. So between us, Spiral Blue, Dandelions, and University of New South Wales. We are working together to launch a smart hyperspectral sensor into orbit. Currently, we're slotted for 2 of these sensors that we're currently working on. And Spiral Blue and Esper together, we're essentially building a smart sensor, as we call it. We're integrating their edge computing and their processing on board our sensor, because specifically with hyperspectral, a major bottleneck has been the amount of data that you need to downlink. So working with Spiral Blue, it's a very valuable partnership with them to be condensing the amount of data that we're downlinking, eventually leading to much more cost-effective and cheaper hyperspectral imagery. Because even if you try to go and buy images now, as referenced in Spiral Blue's previous presentation, it's still very much more expensive, especially once we move into the newer paradigm of Earth observation and once we start doing this chemical analysis. A part of that overall mission is Over the Rainbow. That is our contribution to the Project Rainbow Python. That's where we're building 2 of our hyperspectral sensors that we're going to be launching with them. So just to sort of go more deeper into this, I guess, the specs or like the more details of the overall project. So within the 4 organizations, we've also received funding from the federal government through their AMGC, which is the Advanced Manufacturing and Growth Center. So we've received upwards of $500,000 from them. The total project is around $3 million total combined from the input from all 4 organizations as well as the government. And if we're on track to launch, we're going to be the first Australian Earth observation mission. And that's coming through the collaboration of the 4 organizations that are working on it. And building off of this, our biggest focus is always climate. Especially from Esper's point of view, we started the company for a climate applications. We noticed huge gaps in the imagery data or in data in general available to a lot of these climate applications. And that's where we're looking to fill in those gaps and, remove the blind spots to, I guess, eventually help save the world. But yeah, that's mostly it for me. I think now it might be a good chance to, I guess, open up the floor to questions to ask me, May, and James more about, I guess, the stuff we're working on.
Just for everyone online, you can unmute yourself when you want to ask your question, but let's just take it one at a time. I think we've got one person here in the room in Melbourne, so we'll let Shane introduce himself and ask a question.
I'm Shane Usher. I'm a chemical engineer and chemist and lots of other things. I'm wondering what the frequency range is for your hyperspectral camera. Does it do infrared, UV, or anything like that? And with respect to detecting CO2 and methane and the like, have you verified that you can calibrate this for the low concentrations that you'll see?
Awesome, thanks for that. So with the two imagers that we're launching next year, we're going to be covering the visual to near infrared range, basically going from 400 nanometers to 1000 nanometers. But these are just the demonstrators that we're currently working with. To actually go to the applications that we've spoken about, we do need to expand into shortwave infrared. And that is one of the major key propositions and the key sensor technologies that we're working on in-house at Esper. And for, specifically looking at methane and a lot of these mineral compositions, that shortwave infrared bring out a lot of specific peaks and troughs for those specific minerals. And that's where we're currently building to, have that in-space calibration and the sensor technologies to be actually able to achieve that. This has been proven before, not within us, but we have a number of space missions that we are referencing that have done similar sensor setups in the past. And that's, the studies that we're working off of.
Peter Aylward here in Melbourne. A couple of questions. Number one, it seems like your presentation was, your target audience seems to be a lot of related to mining. Obviously, mining environment, they're sort of a bit of a contradiction in many ways. Tell me about how working with them is going to help the environment as opposed to help them destroy the environment. And my second part of the question is, I think in one slide you indicated you were doing a launch in October 22. Might be outdated. So can I ask what launch vehicle that's on and when you think it might happen? Thank you. Oh, sorry, a third one. So, and then I'll wrap it up. So working with Spiral Blue, are they putting hardware on your satellite to do that on-orbit processing? Yeah, all right. Thanks. Thank you.
Awesome. So with the first question, when it comes to mining, anyone working with oil and gas companies, we see ourselves as a transition technology. Specifically, when it comes to mining, we will always need minerals. We will always need metals. The question with mining, it sort of becomes two-sided when we specifically look at rare earth metals or minerals, or when we look at more fossil fuel focused. So between those, our focus is mostly towards that mineral side of things, helping them excavate more of those actual elements that we need in our day-to-day life to even transition away from fossil fuels that have a much lesser impact. And with, as time goes on, even within mining, there are tight regulations around how the environment or that geology is going to be recovered over time, and that is also something that we're helping with. Everything from initial environmental analysis to what a mine might look like after 10 years after it's completely excavated, and how that entire geology or that geography will recover over time. So those are things that we're helping with. We obviously can't switch the flip off and flip the switch off and not use silicon in our computers, or we just don't have those alternatives existing today. So to aid that transition or even reduce those overall impacts are essentially what we're going with. When it comes to the sensors, we're looking for an April 2023 launch. And currently we're working with hosted payload platforms where we're building the sensors, we're integrating with Spiral Blue's computers, and then we're launching on other people's satellites. So one of the companies we're working with is Sydney-based Space Machines company. So with them, we're looking at a launch with SpaceX in April 2023. And the third question was, I think, around our the details of how we're working with Spiral Blue. So they're while they have them having their own computers, James or May can back me up on this. Them having their own computing systems that will be doing an analysis of our imagery data. We're also going to be using their computer as one of our major payload computers as well. So we're basically, I wouldn't say vertical integration is the right word, but we're very much closely integrating our sensor with their computing systems, and then going much more deeper into that software stack of doing that and post capture analysis of that imagery data.
What's the lifespan of each satellite? Ask my question on the mic.
Sure. So Peter's asking what is the lifespan of our satellite. So with these two missions, at least from our Esper point of view, we're basically building them for a 2-year lifespan for the Project Rainbow Python mission. Mainly because it's a demonstrator, and once we actually get through that demonstrator point of view, we will be building and launching much more mature imaging systems that will be lasting around 5 to 8 years, and that's the lifespan that we're working on. I guess, yeah, James or May, would you like to comment on that?
I think that sounds about right from what I understand. I think the orbit altitude sort of determines that, and I think that's about right. Yeah.
Yeah, and I think around that, we're also going for a low Earth orbit at this point, and even for our planned imaging launches as well, even up to like 2025, 2026, we're also aiming for a low Earth orbit. Anyone online who has a question?
Yeah.
I have a question. Are you only looking at passive radiation from the Earth?
Yes. So our sensor is a passive sensor. So we are going to be capturing light that is reflected off by the sun, which means that we can only image during daytime, or like when the satellite is actually, I guess, not in eclipse. So that's where we're, so yeah, that's the paradigm our sensor currently operates in.
Hello, can you hear me?
Yep.
Hi, Charlie here. My name's Charlie Zerny. And with your aspirations to sort of look at the situation with methane, there is the methane sat program. How does your anticipated project correlate with that, please? And I think methane sat was only one of two systems, but methane sat, I think, had an area of scrutiny of about 100 by 400 kilometres, but it could hone down to about a 50 square metre zone. And it was measuring from even as far down as 2 to 5 parts per billion. So how is your system going to, basically fit in with all that, please?
So within the methane specific, I guess the Earth observation realm, there's, I guess, not even methane sat, where I think right now one of the biggest players is GHG-SAT. Right, recently, I think last month, they launched, I think, 3 more satellites, adding to a much larger constellation that we're working with for specifically for methane monitoring. What we found with working with a lot of our customers is they are currently using methane sat and GHG sats data, but because there's very, like, the amount of frequency that you need to be capturing for all of these oil and gas pipelines across the world, it's basically you want to be capturing at least daily. Now, methane sat is GHG sat. They only had, I think, 2 satellites until, I guess, last month. So now they're building out their capability to be actually capturing that much more frequently. But what we've learned from our customers is that they want multiple data sources. They just they've realized that relying on one operator is not enough to be solving their own problems. And that's where we're looking to be not, I guess, competing with them, but also be, adding to that entire data ecosystem and being a key player there as well.
Okay, thank you for that. And don't mean to throw you into the deep end, but how are you going to sort of compromise or build up an extensive data bank that sort of corresponds to all the seasonal changes that you will get between now and the next couple of years, next 5 years, next 10 years? Is that in your plan too?
Later on, yes, but right now we're primarily focused on building more of a tasking-based system, where essentially we give data where it's needed or in that specific point in time. We do see huge value in that entire historical data, being able to see trends over time. And there's like multiple companies who have built their entire value propositions on top of that. With hyperspectral data, I guess going back to that equation of just being So like even one data cube being so much larger in size that puts a lot of limitations on us, which is why we're primarily focused right now on just that tasking piece. And I guess over time, as we keep collecting that data for the specific customers, that's where it'll actually, after a certain point in time, you'll reach that saturation where we can look at historical trends and do, I guess, future projections off of that.
Thank you. David Boyd, we met before. You mentioned you'll be working in the visible and near infrared initially, and then you plan to spread the spectrum further into the non-visible bands. The wider you make it, the more complex the optics, the sensors, the electronics, the processing becomes. And I saw that you were making your initial sensors sort of in a garage or somewhere. Is that intellectual property that you guys will develop, or is that something you'll eventually have to bring in because in its own right, it'll be a very complex thing? And I'm just curious about whether you've got those partnerships in place and how you're going to go about that.
Definitely, thanks a lot for that. That is, I guess, exactly what we're looking to do at the moment. There's some key capabilities that we recognize in-house, and that right now for us, our key competitive advantage really comes towards how we do the decoding of our hyperspectral data, how our raw imagery created by our optical setup is basically decoded into that data cube, and that's where we've currently, where I guess we're cutting corners on the hardware in some ways, and then we're making up for that in that processing piece, and that's one of the advantages that we come towards. But of course, as we keep on expanding into shortwave infrared, and now we want to be pushing more on the spatial resolution side of things as well, it becomes a much bigger challenge. Everything from having those expensive sensors to be capturing that much deeper infrared light to having much larger telescopes. That is where we're looking to collaborate, and we are working with universities, and I guess Spiral Blue is definitely part of that entire ecosystem as well, where we're adding their processing and their computing systems onto our own imaging systems. So that's how we're looking to build it. But yeah, the core spectrometer piece and that early pre-processing piece is essentially where we're primarily from our end, we're looking to play in from a technical point of view.
One more question. So one more question unrelated to that. I'm interested in the ground segment, how you'll retrieve the data from the satellites, because I suspect you'll be doing a store and forward basis where you'll be capturing huge amounts of data, waiting until you pass over a limited number of ground stations, and you'll have to move a lot of data, even though it's heavily processed on the satellites. I'm just curious if you're using existing ground stations. There are many companies that provide that service. Just curious about that aspect.
So for these initial launches, because those are with hosted payload solutions where we're essentially not doing the entire satellite system, we're not really focused on the technical aspects of that ground segment. That's something that we're paying for by being on the satellite, by paying that's the entire package that we're paying for, everything from actually getting up into orbit to actually down linking of that data, and then basically showing up in like an AWS server. So that's currently how we are planning to do it in the future as well, mainly because it just aces out our operations, because just building that optical piece is, I guess, difficult enough, which is why we're very much focused on just building that spectrometer piece. And then we're, I guess, working on partnerships and other, I guess, and basically utilizing the entire supply chain for specialities to be filling in those gaps. So that's at least how I do it. I guess, James, would you like to, I guess, comment on that in terms of whether you guys are doing something similar, or there's specific stuff that you build there?
Yeah, no, you're right. That's the same approach we've taken so far. We operate as hosted payloads and just use the ground station setup that the satellites are using. I'm not entirely sure what Space Machines has planned actually for their ground stations, but they definitely have something.
Hi, it's Peter again. I think David partly asked my question. It was about receiving data. And once again, it sounds like you're going to wait till you pass over a receiving station in Australia to download that. Or my more general question is, there's so many satellites up there. This is going to be a CubeSat, right? Is there a global network or informal or formal network that can retrieve data from sources on orbit from CubeSats and do whatever they need to do to move it to where you need it to be? That's one question. The second question is, and I think I know the answer, is your business model is essentially, is it selling a satellite service to a business, or is it selling the data that's produced per order from BHP? I want XYZ for a period of XYZ in these parameters, and you say, well, we'll charge you XYZ for that. Is that how it works?
Yeah. So just tackling that data question first. We're basically going for a mix of those two models. So we do see ourselves as like an infrastructure as a service company, where we're building this entire infrastructure of sensors piggybacking on, I guess, other satellite infrastructures. But then eventually the last product that we do end up selling to a customer is the raw data. And I guess just by proxy of that, they're getting access to this entire infrastructure that we're looking to build. Would you remind me what your first question was there?
Oh, it's just about the network and receiving.
Yeah.
And if there's a third party global where your CubeSat receiving network, we've got stations all over the world.
Yeah. So we're a CubeSat payload. So I think the first launches that we're going on are more small sat form factors, but I guess going with that, we do know of some companies building similar, I guess, networks where I think Astrogate Labs, and I think there's, I'm missing their name, but a bunch of US companies actually working towards those entire downlinking problems. Where I guess not too familiar because they are not mainstream just yet. And I guess from a technical point of view, I guess that's basically how SpaceX's Starlink satellites already do that, where they communicate with each other and do those entire downlinking to be, I guess, doing it much more faster and much more efficiently. And just in terms of, I guess, these systems and networks that are already built out, obviously there's, Microsoft's ground station, and I think I forgot what they used to call it specifically, but there's AWS ground station and there's Microsoft's own ground station service as well. So those are also building out for, I guess, ground stations when you need them, and that's what they call them, ground stations as a service.
All right, with no more questions, we've actually finished a little ahead of schedule, so we might be able, if you think of a question later on, put your hand up and maybe we can have a bit
There's still a couple online, I think, with questions.
Oh, okay. Julian, go ahead, unmute yourself. Sorry.
Yeah, good evening.
Hey,
yeah, good, thanks. Just a quick question. I believe you said that your current launch provider is SpaceX?
Yep, they're doing the satellite, yeah.
So if the opportunity arose that there is an Australian launch provider available, would you go with them?
So we're not actually choosing the launch providers for these missions because we're just paying to be on a satellite. Obviously, personally, I'd definitely like to go up on an Australian rocket if it becomes available. And I'm sure that there'll be collaboration options that come up when that does. But yeah, unfortunately, we don't have the choice right now to sort of push that too hard.
No. It's I work for German Enterprise Space.
Oh yeah.
And we're currently in a test phase, developing our first sounding rocket. So shortly after that, we're looking at sending stuff into lower Earth orbit.
Yeah, I'm pretty sure Shoaib and I are familiar with Jarman. So yep, when you get it set up, we'll be there for sure.
Definitely.
Awesome. No worries.
I've got Martin on here. He's got a question, I think. Being very patient.
Do you have a mechanism for ground truth validation of the data that you're getting in these initial testings?
That's a good question. So we do, before we actually go out and do an aerial test, we do a number of soil tests of the area that we're actually going to go and image. This is more from an agricultural lens because that's where we've done some of our initial projects and initial pilot projects in. So basically, based off of that, we then truth it with the chemical information that we got from, I guess, the soil tests that we've done, which are obviously going to be much more in depth than what our imager will be capturing just from a surface level. And then that's one of the benchmarks that we use to be getting as close to those actual chemical tests, because that's essentially what we want to do. We want to do chemical spectroscopy from space, and that's the closest benchmark we want to be getting to, and that's like the biggest ideal there. Of course, we won't be hitting the mark entirety of the time because there are a number of corrections that we have to do on the raw data to actually get much closer to that. And surface level versus, I guess, even 5 feet into the ground is very different, and that chemical composition changes very rapidly. So the other things that we do for our imager validations is just looking at other data sources, essentially specifically looking at other satellite imagery. Sentinel is one of the best sources that we've seen. I guess the most accessible sources that we use to ground truth or like correlate or I guess compare our data with, essentially, our spectral curves, the same that they're seeing. And there's a number of current providers that are out there at the moment that do visual to near infrared multispectral imagery in the 10s to 20 bands. And those are, I guess, also really good data sets that we currently look at to, I guess, overlap our data with them to see how good or bad it is. Cool. I think that's mostly it for the questions, I believe.
All right, thank you for that. It was fantastic, and thank you, Shoaib, and also James and Mehi from in Sydney, I believe, for joining in. Fascinating to see you people working together. It's a great thing to do, and probably you're more valuable as a group than individuals. That group team dynamic, sharing ideas and resources is brilliant. So great to see, very exciting, and really a true inspiration for the whole STEM and space program and development here in Australia. So thank you so much. We're now going to flip. Sorry?
Thanks for having us.
Yeah,
Well done,
pleasure.
Shoaib.
Anytime you're in Melbourne, come on over.
Yeah, thanks. Will do.
All right, beautiful. Back to regular programming. Thanks to those guests joining in. Just going to give you a quick roundup of a few Australian space news items and then a couple of international items. And then we're in for the third superstar of the evening, Andrew Rennie, on planetary stuff. So as you probably saw, Equatorial Launch and NASA conducted Australia's first ever commercial space launch last night. I didn't end up being about 2 a.m. I wrote this before it actually went off, so there's a question mark there, which I sort of removed. So yes, NASA has made Australia's first. So that happened, well, it wasn't the evening of the 27th, it was the early morning of the 27th. This will be followed by 2 more launches, sounding rocket launches on the 4th and 12th of July. So those ones will be conducting astrophysics studies that can only be done from the Southern Hemisphere. That's the reason why we're doing it. The Artemis Space Centre up in Northern Territory is the only commercially owned and run multi-user equatorial launch site in the world. And because it's so close to the equator, it's very efficient for a spacecraft to get into space and hopefully get into orbit. This didn't get to orbit, but it uses the Earth's rotation as helping it to boost up the speed of the rocket itself. So the first one, the one that went off this morning, carried an X-ray quantum calorimeter, or XQC, and a unique X-ray detectors cooled to a frigid 1/10 of a degree above absolute zero to measure interstellar X-rays. And the second will be that one on the 4th of July, suborbital imaging spectrograph for transition region irradiance from nearby exoplanet host stars, or cysteine. I'm sure they make up the acronym and work out the words together afterwards, but anyway. So they'll study how ultraviolet light from stars affects atmospheres of the planets around them. That's interesting. Third one will be on the 12th of July, dual channel extreme ultraviolet continuum experiment, or DUCE. And it'll be studying the so far unstudied part of the extreme ultraviolet light spectrum. Interesting stuff. So that was the rocket on the launch rail before it launched. For those people who watched the launch, it was gone in like a quarter of a second at night time, and it fled the lens out so you couldn't see much, but something happened. It made a lot of noise. So the rocket itself was a Blackbrant 11, sorry. It's a Canadian 3-stage sounding rocket. I'm not going to read every line here. Second stage is the Mark II Mod 5 Telos rocket, and the Taurus motor. Third stage, Black Brant VC motor. Standard payload configuration for the Black Brant 11 vehicles, 0.44 meters, it's 44 centimeters in diameter. You can't trust Wikipedia.
If you go back to the previous image.
The next, this one?
That looks like a two-stage rocket to me. It's only two sets of fins.
Or maybe the third stage doesn't need it.
It's a spin stabilizer, is it?
Well, once you get above a certain altitude, there's no real atmosphere, so you probably don't need the fins.
Yeah, but it still needs stabilization, so it must be small.
Maybe that is. There's 3 sets here. That's a completely different rocket and a completely different location that came from the Black Brant Wikipedia page. This was not a live picture, but it was a picture of a Black Brant. I found it on a GoPro competition video website where people send in unique GoPro images and video. So this is a screen snap of that, of the separation of the, I guess, the third and fourth stages. So you can imagine, I don't know whether you saw the vision on TV of the third stage with the actual instrument. Once the nose cone was off, there's a door at the front of this, opened up, and the actual telescope. Are you going, guys? Thanks, we appreciate it. Showed that exposed the instruments for doing the measurements. I thought it was a pretty cool image. Other Australian space news. Ernst Young, Oceania and Swinburne launched a $3 million space tech hub. They call themselves EY these days. They call themselves Ernst Young. It'll leverage Swinburne's next-gen talent and world-leading technology. And $3 million project is another step towards Swinburne's pledge to build the engine room for innovation and economic growth in Australia's space market. So the EY team is 15 staff comprising of scientists, data and analytics professionals and AI specialists. We'll have 3 major focuses: improving community resilience and environmental health, improving productivity, and creating an ecosystem to solve problems of national interest. Don't we need that? Fantastic. Fleet Space Technologies did launch. It was after our last meeting, so I'm putting it in here. They had a launch of another one of their Centauri satellites. This is the Centauri 5 on a SpaceX Falcon 9 transport missions. These transport missions are dedicated small-sat and CubeSat missions to deploy spacecraft into orbit. It was the company's 3rd launch with SpaceX following a successful deployment of Centauri 4 on Transporter 2 in 2021. So it's a 6U cube microsat, total weight of 12 kilograms, and they operate that in collaboration with Tyvac International. Upgrades include enhancements to mitigate effects of radiation in low Earth orbit, etc. I'm not going to read every line here. This presentation will be on our YouTube channel eventually, so if you want to go through the details, go back to the YouTube channel, just go to space.asn.au, follow the YouTube link, and you'll be able to watch this video there and pause as you wish. So digital beamforming provides extra gain for the new satellite, increasing data rate, also allows S-band frequency channels to be used in different beams. This increases the data capacity by 2.6 times. Interesting, all these different strategies of increasing and improving data processing and handling and transmission. It's great. So they've been using 3D printing to construct its new patch antenna to also feed into development of the forthcoming 3D printed Alpha constellation. And that's going to be scheduled during 2023 for launches. Together, the 2 systems will provide continuous coverage at data rates of up to 520 KB, whatever it is. Kilobits per second, thank you. I thought, yeah, nothing. Constellation enables fleet exosphere system. And once again, they're looking at mineral exploration, et cetera, so helping to work with mining to minimize and make more efficient explosive vibrocesis machines and drilling. Capstone mission, NASA's Capstone mission was going to be launching tonight at 8 o'clock. We were actually going to do a live cross because I believe it's an instantaneous launch at 8 p.m. local. However, it's now 24 hours later, so it's tomorrow night. So set your alarms, kids. So wait for it to progress. Okay, so the Capstone mission will go to the moon for NASA. It's a microwave oven-sized CubeSat dubbed Capstone, never before flown orbit around the moon, blazing a new efficient deep space route that NASA hopes to use for future human spaceflight missions. It's going to take a long while. It'll be launched in initial low Earth orbit by the Rocket Lab's Electron, and then placed in a ballistic lunar transfer by the Rocket Lab's newly developed Lunar Photon spacecraft bus. That's it there. So they're saying, unlike Apollo missions in the 60s and 70s, which took free return trajectory to the moon, this efficient, fuel-efficient ballistic lunar trajectory makes it possible to deploy Capstone to such a distant orbit by using a very small launch vehicle. However, I'm not sure that people are going to be that patient sitting inside a rocket. So this is kind of the mud map of how the launch and orbital maneuvers are going to be. So it's all scheduled to take place tomorrow night, the launch. It'll follow a 3-month trip to the moon. Once again, I think the crew might get a bit cranky after 3 months. And then we'll spend 6 months collecting data around the moon. And that's a picture of it, well, a rendering of it in orbit around the moon. Something a little bit different happened, an anniversary. So I don't know whether you class as Australian Space News, but I'll put it in anyway, so you can have to suffer. June 25, 1967, Our World was first live international satellite television production, which broadcast on June 25. In creative artists include the Beatles, Mary Callas, Pablo Picasso represented 19 nations invited to perform or appear in segments. 2.5-hour event had the largest television audience up to that date, estimated 400 to 700 million people around the world. I think I actually remember that. Australia was the only Southern Hemisphere nation to take part in the program, with 3 segments featured. So the participating countries are right there. Czechoslovakia, Poland, East Germany, and the Soviet Union and Hungary withdrew before the broadcast in protest of the Six-Day War. Opening credits were accompanied by Vienna Boys Choir, and then it went over to the US. Interesting, they had a story about the New Jersey conference between American President Lyndon Johnson and Soviet Premier Alexei Kosygin. However, since Our World insisted that no politicians will be shown, only the house where the conference took place was being televised. The show switched to Canada, various places around Canada, and then went over to Asia, with Tokyo and Japan being the next segment, which is 4:20 a.m. local time in Japan. And then it came down to Australia, crossing the equator, 5:22 a.m. Australian Eastern Standard Time, which was the most technically complicated point in the broadcast, as both Japanese and Australian satellite ground stations had to reverse their actions. I'm not sure exactly what the depth of that means, but for those people who are familiar with the guys, there's someone who definitely knows what it means. Were you involved? Oh, okay. Yeah, so we've got people here as members and online, and sadly some of that with us were involved in the Australian Deep Space Tracking Network for the Apollo and Mercury and Gemini missions. And I believe some of those stations were involved. I do definitely know that the Kubi Creek station was heavily involved on the morning of the 26th. It uses the ATS-1 satellite to both transmit and receive the television. The entire program was live and no use of videotape was allowed. The Australian contribution began with a cross to ABC's Brian King at a tram depot in Melbourne, where the first tram of the morning was about to leave at 5:22 a.m. Very nice. Later, it went to CSIRO Phytotron plant, growing laboratory in Canberra. And then toward the end, it went up to Parkes Radio Telescope in central New South Wales. Kubi Creek served as a link as a temporary guide tower was erected just outside the gate, and the ABC outside broadcast van from Brisbane was stationed at Kubi. So it's not a very big picture, but that's Kubi Creek right there in WA. That's cool. You can see the guy on the truck at Parks. And the highlight for me was the Beatles played. The broadcast took place during the height of the Vietnam War, and the Beatles were asked to write a song with a positive message. And so 8:54 GMT, the Beatles topped the event with their debut live performance of All You Need Is Love, which was fantastic. Now, it was in black and white, so I've got black and white shots. There is a colour picture that was taken in the studio at the bottom there, but this picture here, you can see George Martin introducing, telling the guys, get 3, 2, 1, go from the control room, and then they started doing their song. Actually, I cheated. I do have a little video here. Hopefully it'll play. It only goes about 30 seconds. Now, as I mentioned, the actual broadcast was in black and white. I believe that particular video clip was either colorized or extracted for the Beatles anthology release back in the mid-90s. But it's nice to see him. All right, so that's domestic Australian news and whatever you call that last bit. Some global news. This is me in my astronaut training program a little while ago. So Sierra Space signed an agreement for Dream Tracer to land at Spaceport America. And includes jointly working with application to the FAA for re-entry site license to allow landings there. Sierra Space described the agreement as part of the company's efforts to develop a vibrant, growing and accessible commercial, and also rolling proposed orbital reef commercial space station. So they're building the hardware. This was, people might recall, a proposal by Sierra Space as part of the NASA's commercial crew program. It was eliminated towards the later end of that. However, there's continued to develop the vehicle for crewed operations, but also I think they're doing some parallel development to actually have it as a crewed vehicle as well for that. So there's probably people in the room here that know a lot more about that than I at this stage. They've also got an agreement with the shuttle landing facility. It's now known as the Launch and Landing Facility, operated by Space Florida at Kennedy Space Center, and they'll be transporting cargo, landing it from the space station there. This is a concept of how it will launch on top of an Atlas or something else. I think they're pretty agnostic with their launch vehicle, so they can plonk the thing on anything. And so it's been working to develop, expand sites both within and outside the US. So let's get one landing in Melbourne. What do you reckon? They awarded the FAA awarded Huntsville International Airport in Alabama as a re-entry site, and that'll allow up to 8 landings from 2023 to 2027. And they've also got an agreement with Spaceport Cornwall in England and Japan's Oita Airport. So there we go. China's moon sample mission finds water evidence twice over. So Chang'e 5, I'm probably pronouncing this wrong, and once again I might be stepping on Andrew Rennie's toes here a little bit. They, as people may recall, they ran a sample return mission from the moon, and they've been now doing the analysis. That sample got back, well, it landed on the moon in December 2020. I'm not sure on the date when they got back. Later in the month, there you go. So later in the month in December, by looks. They've revealed that the spectral scan of the surface and analysis of the samples in laboratories on Earth both show presence of water in the region. So there's the concept of the return vehicle blasting off from the moon. That's it on the way back and loading it back onto the return vehicle in orbit, and that's the vehicle landed on Earth. And now, just to stick it in the nose of a few people, China's also aiming to bring Mars samples back to Earth 2 years before NASA and ESA. So people aren't going to like that too much. The Mars Sample mission aims to collect samples on the red planet and deliver them to the Earth by 2031, 2 years ahead of NASA. I'm not going to read all this. The complex multi-launch mission will have a simpler architecture in comparison with the joint NASA-ESA project, with a single Mars landing and no rovers sampling different sites. However, if successful, it would deliver the Earth's first collected Martian samples. So they announced the plans NASA announced plans to delay their Mars sample return and split the lander into two separate spacecraft to reduce overall risk. So the Mars ESA's Earth return orbiter would launch in 2027 with samples that would be returned in 2033. China's mission named Tianwen-13 will consist of 2 accommodations, a lander and ascent vehicle, and an orbiter and return module. Pretty similar to what they did with the moon return samples. All right, been an update on Artemis 1. As people may recall, they rolled the thing back to the pad after an unsuccessful test wet dress on the 3rd. Guys, I'm just going to take a break for 2 seconds.
Okay. All right. Let's see what's Peter's written. But as you know, they had the 4th wet dry rehearsal the other day. I'll just see what Peter's written here. They have actually, after the test, they actually got together and declared the thing a success, even though there were some parts that didn't actually pass. Again, they had a hydrogen leak. They're bringing it into the VAB, and they'll be fixing up the hydrogen leak and a few other bits and pieces and getting it flight ready. And it looks like it's probably a late August, early September. There is a window of opportunity during that time. Sorry, mate. Oh, okay. I'm shorter than Peter. All right. Let's just see what he's got here. Okay, in a briefing on the 24th, they declared the test campaign was okay. NASA plans to perform 1 additional test on the pad of the hydraulic power units. I wasn't aware of that one. The other functions not tested involved de-energizing ground power supplies before disconnecting umbilicals, a step intended to avoid igniting any leaks of hydrogen. So to cut to the chase, the next step is to launch. And that has been years from when they were originally going to do it.
How many times did they use to roll the Saturns out and roll them back before they launched them?
I don't know, Len. Do you know the answer? Really? Okay. This is okay. Len asked the question, how many times did they roll the old 1960s Saturn V's back in after wet, dry rehearsals? And the answer is somewhere between 0 and 1. I think Len was the answer, and 2. So the Saturn certainly appears to have been more robust than the Space Launch System. Absolutely. Absolutely.
But also in its defense of the SLS, I can't believe I'm defending SLS. Hydrogen is very difficult to work with. But there was hydrogen on board the Saturn.
And the shuttles. Yeah. David talked about the difficulty of working with hydrogen. One of the issues that's come up, and I'm probably labouring SLS, was the infrastructure. The ground infrastructure has just not performed. And the reason for that appears to be that the mobile launch tower that they've got, which will only be used for about 3 launches, was actually contracted on a cost plus basis, the usual procurement method that NASA used. And further, there were umpteen number of contractors building it and doing bits and pieces. It was originally built for the constellation program. And all these umpteen contractors, of course, when you find a problem on a tower, who do you blame? Nobody. So NASA, exactly right. So NASA has gone into, having to fix the problem in real time when no one takes responsibility at great cost. It gets even worse, the story of the new Bechtel tower, because they're building another one, because they have to have the Block 1B version of the SLS rocket going. That is now estimated to be worth $950 million and delayed. It will be delayed. It's been going on for 2 years, by the way. And incidentally, if you don't know, over the last 3 months, SpaceX have now up to tower section number 2 of their new Starship rocket. So it's some pretty amazing stuff when you compare the commercial space against the government sector.
So Julian has noted that the Saturn V had a mobile service tower and SLS doesn't. So they probably could fix some things.
That's absolutely true. So Ashley, Julian. No, I'm going to repeat it. Julian has advised us that the Saturn V, you could actually fix it on the pad, because if you recall, it had this huge monstrous tower that used to roll in and out of the Saturn V on the pad. SLS doesn't have that ability. So the only thing you can do with SLS is bring it back to the vertical assembly building. So, that was one of the advantages of the Apollo, and not to mention other advantages as well. Just one of the myths that wander around was when the parts of the Saturn V would come in, Werner von Braun, who was NASA, insisted that they basically tear down the objects that came in and make sure it's okay. And lo and behold, what did they find in some of the stages? Bits of rags, bits of debris. Again, Werner von Braun was all over it. We don't have that kind of oversight on SLS. If you don't believe me, look at CST 100, the problems that they've got there. NASA's kicked themselves quite constantly about their lack of oversight of the programming stuff that caused the CST first flight. Sorry, I'm digressing. Peter, do you want to? I'm just keep talking about SLS. So I could probably do that for another hour, but I'm sure you've got a few more slides.
Thanks, Andrew. As we know, we'll take that as a comment. Tony Jones. Yeah, thanks for that. Sorry, I had to zoom off a second. Yeah, so the objectives of this rehearsal were as listed here. Secondary objectives: demonstrate successfully Kennedy Space Center control interfaces, Marshall Data Operations Center, 45th Space Force, Johnston Flight Control and Mission Evaluation. Collect data from Orion and SLS, mobile launcher configuration loads, cryogenic induced deflection, thermal data and cryogenic load and drain. Validate timelines, collect data from electromagnetic interference, etc., etc. So they achieved a lot of the objectives on this this last, most recent wet dress. As we know, they didn't get everything done, and this slide came out from NASA just recently, which kind of shows most of the things done, but I think you see down the one, test and install pyrotechnics for flight termination. That's going to happen in the VAB. Some of the things they didn't get to do on this particular wet dress was go down to, I think, 9 seconds. And there was I think they were going to start up the APUs and gimbal the solid rocket boosters. I believe they're going to actually do that on the pad before they roll back. So that'll be tick another box off. They did, but they were going to go to T-9, I think, or lower. Yeah, so those, I mean, they think, it's interesting, they said that the APUs in those SRBs have flown before many times, so they're completely confident they're going to work. Mind you, the last SLS, last shuttle mission was what, 11 years ago. So they've been in the shed for 11 years. I'm sure they've been maintaining it. Yeah, yeah. This is silent. It's just a 1 minute and 30-second pan that I noticed them do from the pad, from the mobile service structure. I thought it was nice because you get a close view of the hardware and the interesting.
It's that one that actually leaked. The hydrogen leak was up there.
So once again, this is silent. It wasn't silent on the day, but there was some noggin chatting away, so I got rid of it. It's a big monster. So I believe the two lines on the side are pressurization lines, and the big tube down the other side is the liquid oxygen feed to the engines, and obviously going past the hydrogen tank at the bottom there.
So my question is, does this add space junk?
Does it add space junk? No, undoubtedly.
No, the first stage will re-enter.
The beautiful engines that flew many times in the shuttle will end up in the middle of the bottom of the ocean. So yes, it'll be junk. Are they planning to recover the SABs? I don't know. Like the Eastern Shuttle? They're not.
They're not recovering the SABs.
Fish food, okay.
And just for your information, they're building the expendable version of the rocket engines. It's the RS-25D, and they cost twice as much.
Angelo just remind me the RS-20. What's the shuttle RS-20? Yeah, what's the shuttle ones though?
They were the RNA. They were the C's on it.
The RS-25C shuttle throttleable rocket engines, which flew multiple times. They're reusing them on they're using them on these, and they're going to dump them. Now they're building some new ones that aren't reusable, but apparently they cost twice as much as they originally did. So who knows?
Well, didn't they take the 25As, which were the original shuttle ones, and they put in new flight computers?
Oh, for SLS, correct.
And that made them the C. So it's the A engine, but the C avionics.
So we're having a meeting here, guys. So my recollection, and I couldn't find it, is I did see those 4 engines do an engine swivel during this test, but I couldn't find it on the video. So
There is a video.
Yeah, I'm sure
of
there
the
is.
engine swiveling, and they, in fact, they swivel quite markedly.
Yeah.
You'd be surprised when you see it.
Okay. All right. So what does that leave us with now? I think I showed this last time. This is the Artemis mission availability 2022 and 2023. So there's various color codes here. Green meaning, yes, they get everything they want to get in a shorter time span. Pale green means they get everything they want in a longer time frame. And red means they don't get what they need. So there's constraints on when they can launch for orbital mechanics, lighting, whatever. So that's how to do it. Now, what they're looking at now, all things being equal, they go back to the VAB and they do all the things. They're looking at a late August, early September time frame. I believe I've read somewhere that once they go back to the pad and they charge up and install the pyrotechnics, self-destruct stuff, I think they've got a 20-day countdown clock. If they don't get off in 20 days, they have to roll back and change or recharge the batteries. So, what a system. And for people that aren't familiar, what Artemis is going to do, Artemis 1. What's that? Oh, come on. So this is kind of the uncrewed Artemis 1 mission. They're going to go out, go in the moon, go in a retrograde orbit, and then eventually come back. So I think the mission is that dark green, light green matrix. They're 45-day and 28-day missions in which they can achieve all their objectives. So there we go.
They haven't got the October dates there.
Yeah, October dates are there.
Right to the end of the year.
They go to 2023. Did you read my slides? Too busy looking at your bloody phone, Junior. Okay, so here it is right up to June of 2023. So read it and weep. If we're still here in a year and they haven't launched it, it's going to be pretty sad.
Like the last 4 years.
Yeah. Anyway, so that's pretty much it for international news from me. is Andrew here? Oh, Andrew. I'm going to call up Andrew Rennie and we'll hand over to him. Just take a couple minutes to reconfigure everything.
The U22 and Tianwen and Zhurong. And if I'm not pushed off the stage before that, we might even get on to Perseverance, Ingenuity, Curiosity, Pluto, New Horizons, and some of the new announcements. Okay. These are the plans for the Chang'e series. We've now done Chang'e 5, and you can see that the next ones are going to be getting some samples from the poles of the moon, and that will be before the Americans manage to do that. And in the Tianwen series, well, I'm going to be talking about Tianwen 1 and Zhurong tonight. Ahead of that, as Peter has indicated, they're going to try and do sample returns. And they've also announced plans to go and explore Jupiter and look at the boundary of the solar wind. So that's the planning ahead. Okay, Chang'e 4, that's the landing site. This was taken by the descent imager, and because that probably won't play, no, I've got a backup, which is this one. Now, watch the rover as it moves away from the lander. And you can clearly see the tracks. These images are the Lunar Reconnaissance Orbiter. Okay. Now, that's the lander on the ground on the moon, and I'll draw attention to it several times during this talk. The area is pretty much devoid of rocks. Okay. Here's so this presentation is going to be some of the science papers that have been delivered about the Chang'e 4 mission. And this one was published in Science Robotics. We have the lander and the rover. Notice the wheel and the grid-like structure, which allows the soil to go through it. And the instruments are described here. During the journey, I'm just seeing if that green thing is also on the screen. It is. Okay. Just it's hiding some of the script, that's all. Yeah. What would we do without Ashley? All right. Now, one of the key findings is that the lunar far side is in many ways different from the near side. And one particular thing is the slip and stickiness of the soil. I call it soil. Okay, it's regolith. It's not real soil, but it's regolith. But that's what some of the papers that have been published have focused on. For example, here is how they estimate the slippage. They know how far the cleats are on the wheels, and by looking at the images of the wheels, they can estimate how much it has slipped by. The soil is quite sticky and adheres to the wheels far more than it did on the near side. On the left, we have the rovers for the Chang'e 4 mission, that's U22 rover. And on the right, we have the images for the Chang'e 3 mission, which had the U2 rover. And you notice that the wheel on the right is got no stuff sticking to it, whereas on the left, there's a lot of stuff sticking to the wheels. So that is something that the people who are designing rovers to go to the far side will need to take into account. The Apollo experience on our side is quite different. Here's some more photos of the wheels. And you can see a lot of stuff sticking to those wheels. On the right, on the left, not so much. Here's how that stickiness developed over the days. A lunar day, remember, is a month on Earth, pretty closely. And so this is over the first 5 months, actually over the first several years, because we go up to the 23rd lunar day. The wheels are sinking into the soil by up to several centimeters. So the soils are much more compressible than the more sandy sort of soil on our side of the moon. Of course, if you pushed a wheelbarrow across sand, you know that the further it digs into the sand, the harder the wheelbarrow is to push along. And so you will understand then that driving on the far side of the moon is going to be much more difficult, at least in this area, that area, the Von Karman crater area. Here is the traverse they've made. This is the first 2 weeks, I think. No, first 2 years. Okay, and where they did. And they found considerable differences. The bottom chart here shows the slippage that they've experienced on the various days of the mission. These are the number of lunar days for the first 25 lunar days. And some places it doesn't slip very much at all. In other places, it's very slippery. Now, another paper concentrated on the composition, mineralogy, and chronology of the Mare basalts and the non-Mare materials in the Von Karman crater. Now, just to remind you that the South Pole, which is, you can't see, oh, there it is. Okay, the South Pole's down here. And Von Karman is up here. The Chang'e 4 landed there in the South Pole Aitken Basin. And this is one of the great concentration areas of scientific interest. A lot of CLPS landers are going to go there, the commercial payloads from NASA, and also the Artemis missions will be landing this region as well. So the data that Chang'e 4 has gathered will be of great interest to Artemis. Okay. Again, regional context. A lot of this regional context data is taken from the Lunar Reconnaissance Orbiter and also from the Chandrayaan missions and from the Chang'e 1 mission and also from Clementine and Kaguya, the Japanese mission. So they've used all that data to put together a lot of the scientific understanding of that area. Of particular note, you'll notice up here, we have this crater here, and that's going to feature a bit later down because that impact happened later. It happened after the Von Karman impact. And the material from that is spread right across the Chang'e 4 landing site. Okay, let's go back. And also this crater down here, Von Karman B M, happened after the main Von Karman one. And again, there's debris from this impact, which is scattered over the main Von Karman crater. And Chang'e 4 has come across that material. Okay. From the orbital data, it's been able to map the titanium dioxide and the ferrous oxide. And this particular map, these two maps come from the Kaguya, the Japanese mission. And LT stands for low titanium, and FE is the Feinstein Finsen, so Finsen ejector, the one I pointed to before. Okay. The composition does vary across the Von Karman crater. And the American Lunar Prospector mission has been used by the Chinese scientists to prepare these maps. As you can gather, this American data is very freely available and is used to great effect by the Chinese scientists in planning their missions. The spectral characteristic of different units in the von Karman crater are shown in these images. As in these ones as well. So looking closer at the Chang'e 4 landing site in von Karman, we have maps of ferrous oxide, titanium dioxide, and also altitude maps and compositions. So from that, a chronology of the von Karman crater and the area has been built up. Now, the yellow points, as it noted, there are impacts that are greater than 200 meters in diameter. That's the yellow ones. So this crater is quite big. And from that, a geological map has been prepared. I won't bother explaining all those terms because I don't know them myself. So moving on to another paper in the Journal of Geophysical Research. Again, looking at the geological characteristics of the South Pole Aitken Basin. We've got lunar orbiter material here from the laser altimeter. And the Chang'e 4 landing site is marked in the white rectangle, Okay, moving on to some more topography maps and some interesting features. Notice that the lines moving diagonally across the picture, across here, and the white arrows indicate the northeast to southwest linear features where the topography is elevated. The shading here shows it quite nicely. These are ridges going across this way. And looking at the slopes of the landing area, you can see that it's pretty benign. There's a few danger areas, the red spots, but most of it's green, which is good. It means it's pretty flat and easy to move across. Now, of course, when you take photos in the morning, you get shadows, which highlights these features much better than when the sun is overhead. The ridges have been mapped very nicely, very closely. And so have the troughs. The blue arrows indicate the troughs and the red ones indicate the ridges. Again, this is mostly based on lunar reconnaissance orbiter material. And then we get reflectance mosaics at various wavelengths. The as Shoaib was telling us, the spectra of various materials, like he showed us the apple and how the spectrum can show what it's made of. Likewise, looking at the spectrum of the regolith tells you what it is made of. Also, they've analyzed the craters, those craters I've showed you, and looked at whether they are high in calcium or low in calcium. And it turns out that the distribution of them does vary according to whether they are high or low calcium. Yeah, the size matters in this case. Moving on, the thickness contour of the regolith was estimated based on the lunar reconnaissance orbiter data. This is before the landing. And from crater statistics, they're able to estimate the age of the floor of the von Karman crater by counting craters. The more craters, the older the surface. Moving on. From that, we have a proposed stratigraphy going down in depth from down as far as about 300 meters. It's known what what materials are. We're going to come back to this in a moment with other papers that do look at the results from the Chang'e and U2 mission. But note the age Imbrium refers to the Imbrium basin, Nectarian and pre-Nectarian as you go down. Okay, so topographic mapping and rover localization for the mission. Here are 3 images from 4,000 meters, 100 meters, and 8 meters as the lander descended into von Karman. From the nav cam on board U2, they're able to build up stereoscopic images. And if you can go cross-eyed, you can see those in stereo. There's 2 pairs there. But most people can't do that, so let's move on. It's taken 360-degree panoramas, and I have clipped out of that from this top here, over area here, I've clipped this picture, and from the middle part, I've clipped the bottom one to give you an enlargement. Notice this nice little crater. It's not terribly deep, but it is about 50 meters across or so. And again, we have a digital model of the surface. The land is shown there. And notice that there's quite a difference between the right-hand side of this image and the left-hand side of the image. There's quite a change in the surface there. All right. This is a descent image from Chang'e 4. And on the ground, from that stereo imagery, again, elevation maps can be made and gives us a 3-dimensional perspective. This particular one was taken from that point marked S1 there at on the first few days of the mission. This is from the Lunar Reconnaissance Orbiter camera before and after landing. So for those who don't believe that they went there, well, these pictures are there, they're real. Okay. And this is where it went over the first 5 lunar days. So it's moving most days. It doesn't move every day, but it does trundle along and stops and takes pictures and does analysis of the rocks and things, which I'll mention shortly. So from the descent images, the scientists have been able to count the craters. This helps determine the age of the area. The land is marked there, and the circles mark the craters. And the units across here are in meters. So we're looking at here about 100 meters to either, 150 meters to either side of the lander. They're also able to estimate distances from, this 2 pictures are taken from the lander itself. One is before U2 was deployed, and the other one was after deployment. And they're able to estimate the distances and sizes and things to everything. That's necessary for navigation. From the data returned from U2, they're able to prepare elevation maps, digital elevation maps. And again, you can see most of the area is green, which is safe, but there are a few areas you wouldn't want to go to with a small rover. The nav cam is used to plot the trajectory, where they're going to go. And you can see the center line of the motion is in the yellow line, and where the wheels will go are the white lines down there. So they are using much the same way as they do on the Mars exploration rovers. Remember them and how they're doing it with Curiosity and Perseverance. Now, there are some rocks on the surface. The surface is not totally devoid of rocks. And when they find one, they zap it with a laser to find out what it's made of. And this research letter looks at the dielectric properties. That's the electrical nature of the surface, which is going to be helpful to know how the radar, the penetrating radar works later. So once again, on one of the maps, we have the motion of the rover, and the Chang'e 3 U2 rover as well as shown there, and maps of titanium dioxide. You get all sorts of spectral maps, which we won't have time to look at tonight, but the dielectric constant of the surface material is important for mapping the surface below. And they've also compared the soils at both the Chang'e 4 and Chang'e 3 landing sites with the Apollo ones, as you can see from the map, the graph at the lower right-hand side. Now, they have a radar which penetrates the soil, downward pointing below the rover. And the top picture is the radargram from Chang'e 3. The Chang'e 4 one is much better. Well, it seems to be. Although I think it's more the sites are different, you know, the nature of things. So we have a radargram down here at the bottom, which shows you the different layers. So we're penetrating down quite a few meters down into the soil, finding out what's underneath. So some of the articles that have been published concentrate on the deep subsurface structure at the lunar far side. And here's a radargram. And we've got the waypoints across the top-hand scale here. These are the numbered waypoints that were shown on an earlier traverse that we saw. And here is the time of this signal as it penetrates through. These are in nanoseconds. Let's look at each of these three plots, A, B, and C in turn. First is a radargram. The yellow line represents the aggregated data traces to show the enhanced subsurface echoes. And so we see there are particularly strong echoes, like these horizontal lines. Notice these are the waypoints, 2, 3, 4. So this is distance across along the traverse, going across that picture. Some things are there all the time, like this one here goes all the way across. But some of them have gaps in them, which means that there's something under the surface, but it doesn't extend the whole way. Now, moving on to part B. Using enhancement techniques across the 284 meters of this traverse, certain features now stand out, and they're marked in yellow and cyan. And from that, they're able to work out a stratigraphy, which is the one on the right, going down to a depth of over 200 meters, nearly 300 meters. All right. The signal is attenuated as it goes deeper and deeper down, but that attenuation is pretty much linear. The blue line is the original data, and the others are corrected, various corrections that I won't explain now. And notice that as we go down, depth is across here from 130 meters to 200 meters in depth. There's a few ups and downs, but basically it's a linear plot. So as you go down, the soil is pretty constant in electrical nature, the signal strength in decibels. Okay. Here, this is a little hard to explain, so I won't spend on it too long. That area there is enlarged in these pictures, and these are at different depths. And the colors show the nature of the material down there. So it does vary with depths. As you can see, at this depth, there's a lot of orange area here, whereas further down, deeper down, it's over on this right-hand side. So it does vary. So even though they've only just done that traverse over several hundred meters, they're able to figure out that the surface underneath is actually quite varied. What about the elevation of Von Karman? Here is a transect across that line there. All right. And that's the line that's plotted here, down here, across that transect. Then we've got these ones going diagonally across, and these are the ones that are plotted here. So that's the elevation in the Von Karman crater. Olivine, one important chemical mineral. And there's a lot of, from the Xenu crater, which is about 30 kilometers away from the Chang'e 4 landing site, there's a lot of olivine has been sprayed out by the impact, and the amount of percentage of olivine in the material is shown in this color-coded thing. So notice there's a spray out in this direction, which comes up in the later paper because the Chang'e 4 came across some of that olivine. The waypoints are shown here during its traverse across the floor of Von Karman. 10? 15. Okay. Now, the Moon Mineralogy Mapper is an instrument that was on Chandrayaan-1, Indian moon mission. And that has been greatly helpful in mapping the surface of the surface and what it's made of. So here are some of the results from Chandrayaan-1, which again has been used to help understand the Chang'e 4 landing site. Now, the VNIS, the visible and near infrared imaging spectrometer, or spectrometer, as some people say. And they have concluded from analyzing the rocks that have come across that the materials in the Chang'e 4 site do not have a single source, but rather likely a mixture of South Polar Aitken impact melt components excavated by surrounding impact craters. I've showed you the surrounding craters and the splashed material across Von Karman. Once again, the map showing where they've been for the first 21 lunar days. That's 21 months on Earth. Here are some of the rocks they analyzed and the spectra of each of the rocks, and there's a corrected one on the right-hand side here. So they're able to identify what's in the rocks from the spectrum. Once again, the spectrum, and notice that there's quite a bit of variability in the sample numbers. These samples are from left to right, the first sample they did, then right through to 86 sample. LCP is low calcium pyroxene. HCP is high calcium pyroxene. Now, they submitted in their paper, Zeng et al., 83 images of the targets. Each one was shown. So they photographed it, then they did the spectral analysis of it. And these, I just picked out 2 of those to show you the sort of thing that they were looking at. But there's a little surprise in these. You see what I mean? For those who haven't seen it yet, let's see if I can find them out. There it is. What about this thing here? That's got to be a brick, doesn't it? A brick? This must be taken from the Chinese version of what JPL calls the Mars yard. It's not on the moon at all. At least that's what the conspiracy nutters would say. Anyway, let's move on. Xinyu crater has splash material, and over here you can see that. I keep losing the mouse. There it is. Over here, there's a faint ray of material going out to the Chang'e 4 site, and Chang'e and Yutu 2 has come across that material. Okay. Finsen crater, splash material over von Karman, as did von Karman L. That impact there, splash material this way is shown by those green arrows. And so that von Karman is scattered with material from surrounding craters, which are younger than von Karman itself. All right. Back to that radar that penetrates the soil and working out what's down below. And from that, we have this lovely 3-dimensional thing showing where the rover's been and what's interpreted as being down below there. And so we find that, the unit 1 up down to about 12 meters is lunar regolith, which, by the way, is just broken up rock from impacts and stuff that have happened over billions of years. And then from 12 to 24 meters, the coarser grain materials with some embedded rocks. I indicated that before in this thing where there's materials there which don't cover the whole lot. There's gaps. And so these are the rocks. And then down below, we have layers of coarse and fine grain materials and alternating layers. So this is a new finding. No, the Americans weren't able to do this during the Apollo missions. This is new. Once again, see how clean the landing site is, devoid of rocks. Not many there. And once again, we have analyzing what's under the surface. And this is a comparison between Chang'e 3 on the left and Chang'e 4 on the right. I should say Yutu and Yutu 2, because that's the rover that did these material measurements. Now, from that, you can estimate the thickness of these dark halo craters. DHC is dark halo craters, and the ones that aren't. And if you look closely, I've got some more pictures of those coming up, but some of the craters have got dark halos around them and some don't. Oh, all right. Now I'm going to skip through a few more of these. Plagioclase rock has been found. It's one important finding. Now, unfortunately, the paper is behind a paywall, so I could only get the low resolution GIF images. And let's skip through this because I've got some other things to go. This is the terrain elevation map of Von Karman. And marked here is where sorry, I'm trying, oh, there it is. Okay. There's where Chang'e landed. Now look at the elevation here, 8 kilometers deep, 4 kilometers high on the other side. That's a difference of 12 kilometers. And when that, whereas the Apollo landers, like Apollo 11, could just come in like that, you know, slowly. And Chang'e 3 could also come in at a nice shallow angle. What Chang'e 4 had to do was fly over these mountains and then drop down very steeply to the landing site. Quite a different technology or approach needed for the landing. Okay, right. And this again is shown on the bottom picture there. And the top picture shows the topography. All right. Again, you're looking at different rocks of different spectra, and that helps identify what's in the rocks, and the rocks are quite different. The Indian Chandrayaan-1 has been, data has been used to map, again, what the soils are made of. They've also been measuring energetic particles from the sun. And the data here is quite complex and very detailed, and is something that will need to be considered for the Artemis program. And a lot of CLIPS landers and things are being proposed to also get this sort of data. All right. Now you can see the difference there between a dark halo crater and a bright halo crater. And again, more details on the, some papers have addressed the, what's underneath the soil. And, oh, they found some rather strange rock in one of the craters early on in the mission. And the interpretation is that its impact melt breccia, glass-coated agglutinate regolith breccia. So it set the Twitterverse alight when they found this. But it's nothing, you know, it is special rock, but it's nothing alien or anything like that. Okay. This is interesting. Chang'e 3 had an ultraviolet camera which is able to look at the Earth. Now, do you remember Apollo 16 carried an ultraviolet camera to the moon and took photographs of the Earth? Well, it's been doing the same. I haven't seen any from Chang'e 4 published yet. This is from Chang'e 3. Now, quickly to Mars. Okay. Well, it's been roving around the place, the map showing where it's been. And by May the 5th, it had been working for 347 Martian days and traveled nearly 2 kilometers. Since then, it's been resting because of the winter and opposition and all sorts of factors. And it's going to be revived again in November. Just like the Americans do, they've named little rocks and things in the neighborhood with Chinese names to help them say, well, look, we're going there and we're going there. They're not official names. They're just names that they give small features. You're allowed to do that when it's less than a certain size. I think it's several hundred meters across. Zhejiang again is using autonomous driving to avoid hazards. And you can see here it's gone around a rock. And they've got this laser which zaps rocks and vaporizes it, and then they analyze the rock. They found evidence of recent aqueous activities on Utopia. again, they've got analysis of the materials. And these are some of the spectral observations that have been made of the rocks. And they show, I think I've got it here, yes. What's happened here is, at some stage it's been wet and the materials have compacted and then it's been eroded away. And these planty rocks are left behind where they're more resistant to erosion. So that's been evidence of episodic fluctuation of the groundwater at the landing site. Just like Spirit and Opportunity and the Insight lander, dust is a problem, but Zhurong can fold its wings and presumably, hopefully some of the dust will fall off, which the rovers, the American rovers can't do. They've released 3 Wi-Fi cameras, one on the way to the to Mars, one Zhurong put on the surface, and the other one was released late last year, and it drifted away from Tianwen-1. It took a series of photographs, which are useful because it allows the mission planners to see how their spacecraft is going. You know, are all the things out properly and everything? So, but it makes me wonder, okay, so there's 3 cameras we know about so far. Are there any more? We don't know. All right, quickly, Ingenuity. It's been flying across this SAA dune field, whereas Perseverance had to go round to the top of the picture. There are all the flights that it's done so far, 29 flights. Amazing. I've highlighted a few of the major ones that included the most distant and the fastest. And the most recent flight was on June 11. And it's now near the, let's go back quickly. It is now over here. The rover has been around here and is now way over here somewhere. It's gone up into this area here. And the helicopter, having zigzagged across, is sitting over here somewhere, okay? Now, on the flying across there, they said they were not going to go near the material on the ground, the artifacts on the ground, because it would upset the navigation of the helicopter. But then the people who, you know, the engineers have said, no, we want to see how it survived. And so the helicopter people said, okay, we don't like this, but we'll do it. And they flew over the materials there. And so we have some pictures of the back shell and supersonic parachute. They've been digging samples, and there's an environmental plot of Jezero, and this has been released just recently, showing dust devils on Mars. Okay, 2 of them. All right. Meanwhile, in Gale Crater, Curiosity has been wandering around there for 10 years next month. 10 years. And it's discovered lots of things, but it did come across these jagged rocks. Now, the jagged rocks are not good for Curiosity. These wheels are much worse condition than what they're shown in this picture. They've got holes in them, and some of those cleats and things have fallen off. And when they came across these gator rocks, those sharp rocks, they said, we're not going to drive across them. We're going to go around. And so they've gone around. And I love this picture because it's a nice little landscape across Gale Crater. There, okay. And they've been digging in there. And lastly, we're out there in here now. It's a nice picture of clouds. They do have clouds on Mars sometimes. And InSight, poor little InSight. Look at the power. 500 watt hours, so 5,000 watt hours per day at the beginning of the mission, and now it's down to about 500. And that's why the mission's going to end very soon. Okay, and there's a sunrise as seen by InSight, and we say goodbye to InSight as the sun sets on it. Okay, I love sunsets on Mars. All right, they did get a big earthquake on May the 4th, and the biggest one they've had so far. They've had a whole lot of little tiny ones before. They're about 1,300. And there is a movie of that, but it doesn't show in PowerPoint. And I think we better leave it there. Okay, so I was going to talk about Mars, Pluto, and some of the results from Ryugu, but July 12, but that's not planetary. Well, it can be planetary. James Webb can take planetary pictures. All right, well, I better hobble off the stage.
Thanks, Andrew. That was fantastic. And with that, we conclude tonight's meeting. Thank you so much for coming to the meeting, for coming up online, and also particularly for our speakers, both here in Melbourne and also from Sydney. And so we'll see you again. I think it was July 27, was that the date for next meeting? I'm not sure what the schedule is. Our meeting coordinator, Michael, is not available this week, so he'll be back, but he'll be doing all the stuff in the background. So we'll let you know well in advance what's going on. And thanks very much. We'll have a good month, and we'll see you next month.